So in most fields of optimization, the focus is mainly on convex optimization. But in this talk, I aim to address the often much more difficult non-convex optimization. So means of optimizing, which means either maximizing or minimizing non-convex objectives. And to simplify things, I'm going to just be speaking in the terms of unconstrained non-convex optimization. So we won't have any constraints on our objective other than some box constraints. So we'll bound our variables between some static constants. But besides that, we have no constraints. We're going to first define what it means for an objective to be non-convex. And in order to do that, we need to look at what it means to be convex. So this is the formal definition of what it means for a function f from Rn to R to be convex. So this is the formal definition. You can read it if you like. I'm not going to spend too much time on it because it's a little bit hard to tell what this is doing unless you're quite familiar with this already. So really what this is saying is that if f is convex, then we may select any 2 points in its domain and have the line passing through those 2 points lie on or above the graph of f. So this animation perfectly illustrates what this is talking about. So any 2 lines from any 2 points on the graph will always be above or at it. And so that's a really nice visualization of that right there. So conversely, the non-convex objectives do not have this nice property. So here's an example of a non-convex objectives, and you can see that there's many instances where parts of the line dip below the graph, which indicates that it's not convex. So that means this is going to be a very difficult problem to solve. Especially when we talk about the n-dimensional setting. So this is only one dimension, right? Only one number is the independent variable x. So we don't consider this to be especially hard, but once we scale up the problem to n dimensions, it's going to be quite difficult to solve. So certain convex problems have a multitude of quote nice properties, not the least of which is that we can be assured that if the gradient of the objective is 0, then that will give us the global optimal solution. And with that, we can have very many certificates of optimality, so that we can be sure that this solution is the exact global solution, and that there's nothing better than that. So conversely, non-convex objectives don't have these nice properties. We may find a local minima, any one of these really, but we have no way of being sure that they're optimal until now, I guess. And that's the point of this talk and my paper that I've written, which I'll attach in the description, the repository to this presentation, as well as all the code for all the other things in addition to what you can see here, as well as the paper itself. That's a little bit of background for what it means to be convex and non-convex. But how does this apply to the real world? So many real world problems are non-convex. So we need to find a way of optimizing them, because these are real problems that we need to solve. Not every problem in the real world has the luxury of being convex. In fact, many don't. So I guess the example we're going to be using throughout this paper is parameter fitting to a model. So we're going to have certain data points in a model, such as this one right here that you see, a sine bx plus b cosine ax, and we're going to want to fit the data to this model. We're going to find what parameters give us the best fit. So we generate this picture here. So I'm using a equals 4, b equals 6 right here, and that gives us this picture. And then I'm generating some random noise over a normal distribution, and we're going to try to fit this data to this curve here. So the way we're going to do that is we want to minimize this L function. That's going to be the difference, the least squares difference between the vector which contains all of the data points and the objective function itself. So we want to find the place where the length of this difference vector is smallest, and that will fit these data points the best to this model. And if we graph this, this is the graph of L, the loss function here, and you can see that it's quite complicated. There's a lot of local minima. You can see I've plotted the true minima in that white dot right there. That's going to be not very easy to find unless you were quite close there and starting with gradient descent or Newton's method, and you started right next to that white dot there. So we're going to need to find something a little bit better to optimize this. So this is a bit of a motivational problem here to see, that yes, indeed, we do have these non-convex optimization problems, and we need to solve them because they can be quite useful in the real world. And we'll be solving this one and more later on. But first we need to introduce a couple of groundwork algorithms here that are going to help us along and give us an idea of how to do this. So the first thing is a uniform grid search here. And let me just change one thing here. I wanted to double check this, but I think I already did. So good there. So uniform grid search is a bit of a naive method, but I'm going to display it anyways because it sort of lays the groundwork for what we're going to be talking about next. So we need to impose some restrictions on our objective f. So we assume that it is continuous, first of all, and has bounded slope. Notice we don't need it to be continuously differentiable everywhere over its domain. It's good enough that it's continuous and has a bounded slope. Bounded slope, i.e. that means it is Lipschitz. That's what that means, over a rectangular set. Those are our box constraints. And you can see the definition of Lipschitz right here for one-dimensional objectives. So that just means we have bounded slope. So if we took f of x minus f of y, divided it by the difference of x minus y, that's less than or equal to some constant L, which is going to be the upper bound on our slope. And later the gradient when we deal with Rn objectives. So the premise of uniform grid search is fairly straightforward. We partition our interval that the function is over into k subintervals. K subintervals of equal length with endpoints x naught through xk. So we have this inequality here. So these are all our endpoints for our subintervals. And we let this z sub I be f evaluated at x sub I for any I in our collection 0 to k. So objective f is Lipschitz, so we have this property right here, like I've said. And then if we did some algebraic stuff, we come up with this right here. We can split it up into two inequalities because we know that x is inside this interval here and is greater than this value right here and less than this value. And then if we add these two inequalities together and do a few extra algebraic manipulation steps, we get this right here. This is what we get, and this is sort of this forms a lower bound on our objective, which is helpful because we know that this will always be lower than our optimal point, or at least equal to it. So that's very important that we have a lower bound on our objective f. So this is the premise for this optimization technique here. So here's the Julia code, which is going to run this method. So we're going to partition this function a bunch of times, or this interval a bunch of times, evaluate the function there, and it's going to this lower bound is going to sort of converge to the optimal value quite slowly, especially as we get closer. So this is our lower bound is the blue, and the upper bound is the orange. And that gives us this solution right here, which is correct, right there. And this is kind of a picture of what's going on here. I'll wait for it to start over. There we go. So you can see the orange line is our lower bound, and it's approaching the minimum of this non-convex objective here. And as you can see, this is slowed down obviously, but as you can see, it does get a lot slower towards the end there. It becomes harder to find the solution as we get closer to it, because we're partitioning this interval into k different subintervals each iteration. And that's kind of a bad way to do it. It's rather inefficient. But it lays the groundwork for what we're going to talk about next. So that's uniform grid search, and that's a way to find the minimum of a non-convex one-dimensional objective like we have here. So this gives rise to a bit more sophisticated of an algorithm, still for the R setting, only one-dimensional, but it's a lot more sophisticated. It's called Payovsky's algorithm. And this is an old algorithm that I found in an old Soviet paper from the 1970s, and it really was what motivated this whole discussion on optimizing these non-convex objectives. And as far as I can tell, it really isn't used anywhere. And I guess we'll see why in a little bit, but we'll try to make sense of what it's saying mathematically. And in the thesis defense, I go into a lot more detail on this method as well as the next one, in terms of the proofs, because the proofs in the original paper are quite difficult to understand, either due to the writer himself or the translation, because it was originally written in Russian. But anyways, so Payovsky's algorithm is a deterministic algorithm for optimizing any one-dimensional objective f, which is Lipschitz over some interval AB. And it works by bounding the f star, the optimal value of f, between two monotonic sequences, one which converges to f star from above and one from below. So the first sequence, which we'll call a sub k, is generated in the following way. So we take intersections of lines with slopes plus minus L that pass through these points. And noting that L is the Lipschitz constant of f. And these intersection points, which will denote x hat sub n and alpha hat sub n, will always be below f, due to the fact that f is Lipschitz and L is the Lipschitz constant. And this is proved in the thesis as well. So taking the minimum of all these intersection points gives us the next value of alpha sub k. And we generate beta sub k, the second sequence, which converges to f star from above, by evaluating f at the x hat sub n, which generated alpha. And this is a picture of what this is talking about, because that's a little bit hard to say with just words here. So you can see that these lines right here, I'm looking at the right one, the rightmost one, the dotted lines. That is a line with slope minus L, and to the right of it is a line with slope plus L, and you can see it's passing through points x1 and x2, intersecting at point alpha down below there. And alpha forms a lower bound on f star, which you can see there. And if we evaluate f at the x which generated alpha, we see that we get beta, which forms an upper bound on f star. And yeah, interestingly, these two subsequences, or not subsequences, sequences rather, will converge monotonically to f star from below and above respectively. And using this, we may check whether or not the value of beta sub k minus alpha sub k is small enough. And we may use this as a sufficient certificate of optimality for these non-convex objectives, which is quite incredible. So, in fact, this technique generalizes quite nicely and is proved in the Rn setting. So this is quite an interesting result here. However, implementing this procedure programmatically in the Rn setting is quite difficult. And finding any implementation at all, let alone one that is remotely efficient, proved to be quite a difficult task. And we'll see that a bit later. But for now, we're going to be showing just the implementation in the one-dimensional setting, which is quite fast. So that's what this is doing. This is the code for that right here. So you can see I'm hard coding the intersection point between these two lines right here, up above. And this is, you can see some resemblance to the uniform grid search bound that we saw before. So that's kind of where this comes from here, from the Lipschitz continuity of F. So yep, this is the implementation of that, and this is a little method to sort of animate the solution so we can see it more clearly. Here's an example problem down here. Very nice convergence we see there. You can see the purple is the alpha, red is the beta, and on the right there and on the left you see the sawtooth approximation of the objective in blue there, and that gives us a really nice solution, obviously quite slowed down there so we can see it. And I have a couple other objectives here just to showcase different scenarios. This one's pretty similar to the one we just saw. Nice convergence we see there, maybe with a bit more, higher of a Lipschitz constant. Oh, and it's worth noting too that the Lipschitz constant need not be exactly the true L which works for this objective. It could be just an overestimate. As long as it's not less than the true L, you may choose any L which is greater than or equal to it. And that the overestimate, depending on how much of an overestimate it is, will be slower, but it will still converge just fine. And this can be useful in more complicated objectives where it's not practical to find what L is exactly. We could take some sample points or something and maybe add a little bit of an overestimate to that to get a valid constant there. Moving on to the next example here, this is just sine x. I wanted to show an example with non-unique global minima here, so you can see it does bounce between them depending on which sawtooth approximation is smallest, that iteration, but it still does converge. You can see that. Kind of an interesting picture there. And then a bit of a silly example, but I have a constant function here, and you can see the same behavior. Obviously the Lipschitz constant here is going to be just 0, but since that would cause some problems in the algorithm, I've set it to be just a small number close to 0, so we can see what's actually going on here. And I suppose if it were exactly 0, we could say it just converges immediately to the solution, but obviously we know that since it's a constant function there. We got kind of an interesting stair-stepper convergence on our alpha beta though, which I think is kind of interesting. Okay, so that's Pajovsky's algorithm. That's the one-dimensional version of what I'm about to show you. So this is my own implementation of the n-dimensional case, and it's going to be a little bit complicated in terms of the implementation. If you're interested, you can look at the code, which I've linked, and you can see my implementation there. There's a couple of different ways I do this. So this is called cone search. So yes, like I said, it's the n-dimensional generalization of Pajovsky's algorithm. However, instead of taking the min of intersections of lines, we rather construct a series of cones. And I'll go into some more visual details on what this exactly looks like, but for now we define a cone as this right here. So g of xy here is our cone, and y being its peak. I guess y is the location of the cone, L is the Lipschitz constant, and then we're using the infinity norm to sort of generate this. So you can imagine a point at f of y and then sort of a cone shape emanating from that going down. And if you want to see what that sort of looks like in the one-dimensional case, you can see instead of looking at these dotted lines as V-shapes, look at them as mountaintops. So you can see each mountain peak represents a cone in a way, a one-dimensional cone. So then to really sort of make this more tangible, I've written an implementation of this in Unity, the game engine, to sort of get a more visual approach. So I'm going to pull that up now. And this was quite complicated to do, but let's just let it run here, and then we'll see what's going on after that. So we're going to let this run here, and then I'll sort of walk through what's going on here. So for the sake of simplicity, I'm optimizing x squared plus y squared here. Obviously that's convex, but this will work for any non-convex objective, as I've proved, but it just choosing a non-convex objective in this setting only serves to be confusing visually speaking, since there's a lot going on here. So you can see I've generated this x squared plus y squared with this like cloud of points, I suppose. And if we zoom in, we can see the supporting cones. So each one of these cones in all the different colors, I've just made them different colors so that they're easy to see, have sort of their peak, which evaluates at the function itself. You can see, like, for example, this orange one, its peak is precisely at the objective value there. And these red dots correspond to the intersection points of these cones. And this is why I picked the infinity norm for this, because if we pick the 2 norm, these would be circular, and we would have infinitely many points where these would intersect with another cone. But since it's the infinity norm, we can represent these cones as simply 4 planes, and which turns this into just a linear system which we can find the intersection with. And you see that represented by all these red dots. And the minimum of all these red dots represents our new alpha, that iteration. And here I can actually, let it run a few more times. So you can see at each min intersection, it's generating a new cone and finding more intersections there. Obviously, this is slowed down, so we can see what's going on there. It's finished, and look at that. We have more cones. I'm not doing very many iterations here, but if I were to continue this, these cones, their peaks, I suppose, would collect in the region surrounding the optimal value of this objective, and the peaks of these cones form a valid upper bound on the optimal value, beta. Those are our beta values, converging monotonically to the optimal value, as I've said. And these red dots, or at least the minimum of them, represents a valid lower bound on the optimal value. Those form our alpha values. And as I've shown in the paper, these converge monotonically to f stars. We kind of can squeeze it between that there. So hopefully this lens, this visualization is helpful in sort of seeing what's going on here. I hope it does. Anyways, let's go back to the notebook here, and we can continue. So now we're going to use cone search to solve that problem which we spoke of in the beginning of this presentation. If you remember, we had our model, a sine bx plus b cosine ax, and we generated some data points around it, some noisy data points, and we generated this loss function with the solution at 4, 6. And now we can have a means of actually solving this in I suppose R2. And it's non-convex, and we can be sure that it's the right solution, which is kind of interesting. It's worth noting that the true solution of this loss function will not be precisely 4, 6 due to the random generation of the points which we have. It'll be something very close, and that estimation will get closer as we add more data points. But we're merely trying to fit these data points to this model, so the true solution of this loss function won't reflect exactly what the parameters originally were, 4, 6. With that said, I implemented the cone search method in Unity, which uses C# language, as I've shown. But in order to get a lot more speed, I wrote it in Rust as well, which took quite a long time. This was a difficult thing to do. But anyways, this is I'll briefly show the Rust code here. There's a lot going on. I'll have this linked, the repository for this. But this is essentially doing the same thing as Unity, just a lot faster. Yeah, I'll happily answer any questions you have about this code. as well as ways to make it better. Let's keep going here. So I've already solved this problem in this Rust implementation, exported the output to a CSV file, and I'm reading the CSV in here. And here we see the first limitation of this method. So in R1 up here, I'll go back to this picture because it's really telling here. In R1, we know what lines we need to intersect with which lines. We know that the line all the way to the left won't intersect with the one all the way to the right. At least we won't care about that intersection. So we're only going to consider the lines right next to each other as valid intersection points. And we know that because they're right next to each other. Obviously, they're the one or two lines removed wouldn't give us a valid intersection. But in the RN setting, we don't actually know which cones are going to give a valid intersection without a lot of computational work. So that's the first and probably the most major limitation of this method, is that we don't exactly know which cones are going to be close enough together to form a valid intersection, and this causes this algorithm to be somewhat slow. And I do believe that there is a better implementation of this, but as this already took several months to develop, I'm going to leave it to others that are smarter than I am to figure that out. But for now, you see it did solve it. Here we get something close to 4, something close to 6 right there. So that's good to see. This is the runtime, almost 80 seconds, which isn't great, but it did solve it, which is very cool. It solved it deterministically. We can be sure that this is correct because I'm using I forget exactly what I was using, but I was using an alpha beta tolerance, so beta minus alpha value. So this stopped when beta minus alpha was small enough. So I have a reasonable, I can assume that within that tolerance, this solution is reasonably correct, which is pretty cool. And then here I'm just graphing the iterative improvement of this algorithm here. So you can see, yeah, it's not quite exact here. I think the tolerance is pretty high because the time constraints on this algorithm are not great, but it does get a pretty nice close solution. At the very least, starting here with Newton's method or something would probably yield the right result. So that's nice to see there. And so that's cone search. And as I explained in the paper, as I just said, I think there's a much better implementation of what I've done, which is possible, which would make this practical, I suppose. But for now, we need to only we need to maybe consider it more of an interesting algorithm in theory, perhaps not in practice yet. I do think that someone might be able to find a better implementation than what I've done. But for now, this is the best that we have. And as I said, I haven't found any other implementations of this. I haven't really seen this algorithm discussed anywhere. I'm not sure many people are aware of it, which is why I picked it. It seems like an interesting topic. It's an old algorithm. Like I said, it was developed over 50 years ago by a rather unknown mathematician in Russia. So I think that, and he only developed it for the R setting, and here is the generalization of that, which is why I sort of thought it would be an interesting topic to go over here, especially since it's so useful in theory. But that brings us to another method of optimizing this sort of thing called basin hopping. And unlike our cone search or Pyofsky's algorithm, basin hopping does not have a proof of convergence. It does not have any assurance beyond a shadow of a doubt that we have reached any optimal solution. What it does have, though, is speed, ease of implementation, and very scalable structure. It scales quite well to Rn, and it's easy to implement, and it's fast. So it checks all of those boxes except for the proof of convergence. And for that reason, it's used very often in practice to solve these objectives, these non-convex objectives, to great success, right? Because in practice, often you don't really care if the solution might not be correct, as long as it is 99.9% 99% of the time, then usually you'll be okay. So anyways, let me go over sort of the procedure for basin hopping here. It's a fairly simple algorithm. You first start somewhere in the objective of f, and you minimize locally using something like Newton's method or maybe gradient descent. And then you take sample points in the neighborhood around this local solution. So we have a search length, which we'll call L, and you will randomly generate points in this around the solution with radius L, and you'll pick one based on some certain criteria here. So you see that this right here is called the Metropolis acceptance criterion, and this is one of the most common ones that are used to accept a new point as the next, I guess, valid starting point to continue the algorithm from. So this is how it works exactly. So say we have x star, which is our old optimal value, and x hat star, which is our new optimal value. So if f of x hat star is less than f of x star, we accept it right away, right there. Accept it right away. But if we generate some c value between on the interval 0 to 1, and that's less than this probability curve right here, then we still accept it. So we might have this might be greater than this, or greater than or equal to that. But if this is satisfied with a random c value between 0 and 1, then we still accept it. And this is to prevent certain unwanted behavior, especially it helps prevent us from getting stuck. I guess it's just a thing that people have developed to combat that. And also t is just a parameter here, so it's sort of the steepness of this probability curve. And this is a little visualization of that. So on the y-axis we have c, which is the height here represents our random value between 0 and 1. On the x-axis we have the difference between f of x star and f of x hat star. And you can see if f of x star is greater than f of x hat star, meaning this difference is positive, then you can see we accept it automatically. That corresponds to that vertical, or that horizontal rather, blue line there. And as that difference becomes wider and wider and more negative, the probability of accepting that value becomes less and less. And you can obviously adjust the height, or the steepness of this curve rather, by adjusting the t parameter right here. Right there. So that's sort of an overview of what basin hopping is doing, and there's other much more sophisticated implementations of this. But my implementation still works quite well, and I'm going to showcase that here. So this is just initialization. You can see there's a lot of parameters. Basin hopping has a lot of parameters. And interestingly, the search length L, which I've mentioned, that's not going to be static. We're going to scale that dynamically. So how we're going to do that is we're going to track the rate of acceptance, so the rate at which we accept any new solution as the next best solution. So if our acceptance rate is low, or less than some target value, say 50% or so, then the algorithm is returning very few better solutions. So we scale our search length up to get a larger search area. And conversely, if the acceptance rate is too high, then we may be trapped in a basin. So we scale, there's a typo here. So we scale our L value down until the target acceptance rate is reached. So yeah, so now we're going to use basin hopping to sort of solve the problem that we've been working through, which we had already solved with cone search. Now we're going to solve it with basin hopping here. So you can see we've run it. It's taken 23 seconds, which, we got unlucky there. Usually this takes much less than that, especially for R2. And I've seen it take as low as 2 or 3. And like I said, this is only my simpler implementations exist which can do this in a small fraction of that. So, but anyways, we see we get a very close fit here to our original parameters, 4 and 6. So 4 and 6 are our original ones. We can see we get very, very close to that there. And then here I'm plotting the original curve with our best fit curve in blue, and you can see it's quite close, which is really interesting to see there. So moving on, we can solve more difficult problems. So here maybe we want to have a few more parameters. In this case, just one more. So we maybe want to model some population data with the logistics equation here. So we define some parameter vector P that contains all our parameters and our loss right there. So then we minimize this loss function, which I've already shown. That's just a reminder here. And you can see we generate this sort of population spread here, and these data points, red being the true curve. And then we solve it with our basin hopping implementation here. Let's see how long that took. Let me scroll to the bottom. Quite a long time, actually. Not great. I've been getting kind of unlucky, I guess, with these stochastic methods for these tries here. Normally this takes less than 10 seconds, but regardless, it did find a good solution. You can see that there, and then we get our best fit curve right there, which is quite a good fit considering how complicated the loss function is. Let's do another one. I think the sine cosine model yielded some interesting looking results. So I'm doing one more parameter there. So I'm adding a C parameter here and another sine term there. So we have a three-dimensional objective. Here's what our curve looks like, and I've generated some data points. And it's interesting that these data points are very widely spread, right? Like it's tough to see what's going on, but very interesting that we can still find a good fit here. So then here's our loss function, and since we have three variables, I'm adjusting C as our third variable sort of dynamically. So you can see kind of what that looks like. C is just oscillating between -10 and 10 there, and that's giving us sort of a picture of our loss function. And I have plotted the A, B values, which give us our best fit parameter here in white. You can see that, and that's for some C value. I don't remember what, or this is generated randomly, so I'm not sure what that would be. But we'll solve that in a second. So that's our loss function right there. So then we solve it with Basin hopping here. See that it only took 13 seconds to solve that one, so that's good to see. You see we get a great solution, very, very close to our true solution, which this is the solution to the loss, which minimizes those distances that we saw, and see just a great fit here for this. You can see that we can barely see the true curve in red. Very, very nice fit there, especially from such a wide range of data points. And so then, as I alluded to, better solutions or better implementations of this method exist. So I'm just going to show one of those here. So this is not my implementation of Basin hopping, but it will come up with a solution in a much more timely manner, just due to the fact that this has been worked on for years and by many different people. So here's like the generalization of the model which we were using before. So here I set k equals to 10, or 5 rather, which means there's 10 different parameters, right? 5 A's and 5 B's right here. Then I generate our noisy data. We get this curve, 10 parameters. We solve it using one of these external packages, and we get our fit there, which actually it looks like it didn't quite do as good a job as I would have hoped of fitting this. Still not bad though, especially considering the number of parameters. And these stochastic methods I've said are quite a bit faster than the cone search implementation, which I showed before. But my hope is that a faster implementation of that could be found, because it's quite interesting and powerful in the mathematical sense for finding these non-convex solutions, or these solutions to these non-convex objectives, rather. So while my implementation of cone search maybe isn't as fast as it needs to be practical, I do believe the mathematics is sound, as you can see in the proofs of this of the convergence there, and as demonstrated practically, it does work, just a little bit slowly. So yeah, my hope is that a better implementation of that could eventually be found, and we could sort of move away from these stochastic methods, which do work quite well, but aren't deterministic by any means. So yeah, thank you for listening. If you have any questions, I'll be happy to answer them. Like I said, I'll link all my code in the paper, in the description, so that if you're curious, or if you have any ideas on how to make this better, you can go look at that. And yeah, I'll even be happy to talk to you if you want about any sort of improvements you think could be made. But for now, that's it. So thank you so much for watching.